All right, let's dive into something truly monumental today. Welcome, deep divers, to an exploration of the universe's most extreme enigmas, black holes.
Hmm.
These aren't just fascinating curiosities from science fiction, right? They are fundamental cornerstones of our cosmos, these cosmic laboratories that push the very boundaries of physics as we know it.
Absolutely. They really stretch everything we think we know.
So our mission for you, our dedicated listener, is to navigate the profound complexity surrounding these objects. We want to distill the pivotal insights from a wealth of incredible sources we've looked at.
Yeah, there's a lot out there.
We'll trace their journey from, well, surprising theoretical whispers, all the way to groundbreaking observations and confront the biggest mysteries that still baffle physicists today. Prepare to have your understanding of reality stretched.
It's truly remarkable how black holes, once considered these abstract mathematical constructs, have just transformed into central figures in our cosmic narrative.
Completely.
They fundamentally challenge our understanding of space, time, and, well, the very nature of matter.
Mm-hmm.
Over the course of this deep dive, we'll journey from their unexpected theoretical birth, often emerging from equations before any hint of physical reality, through their profound implications for everything. From the fate of stars to the grand formation of galaxies.
Right.
And we'll also grapple with the most significant questions still at the bleeding edge of science. My aim is really to guide you through this intricate landscape, offering a comprehensive yet clear understanding, sidestepping the really dense jargon where we can.
Good.
We're going to see how these extreme objects serve as the ultimate tests for the laws of physics.
Our story begins, as many great scientific tales do, with a revolution. For centuries, Sir Isaac Newton's law of universal gravitation back in 1665 had painted gravity as this simple, attractive force between masses. Pretty straightforward.
Right, action at a distance.
But then in 1915, Albert Einstein unveiled his general theory of relativity, and the cosmic canvas was completely repainted.
A total paradigm shift.
He didn't see gravity as a force, but as a manifestation of the curvature of space-time itself. I mean, just imagine that. Space and time aren't just a static stage for events. They're dynamic participants being warped and stretched by mass and energy.
It's mind-bending.
This was such a radical departure from classical physics that, at the time, the mathematics were considered incredibly daunting, and it was widely believed that only, a tiny handful of scientists could truly grasp its profound implications.
Indeed, Einstein's theory introduced a paradigm shift of such magnitude that it truly required an extraordinary mind to begin to unlock its secrets. And this brings us to the poignant figure of Karl Schwarzschild.
Yes.
Astoundingly, a mere year after Einstein published his General Relativity in 1916, while serving on the Eastern Front in the German army during World War I.
In the middle of a war.
Right. Schwarzschild produced the first exact solution to Einstein's notoriously complex field equations. His solution, which now bears his name, the Schwarzschild solution, provided a precise mathematical description of the gravitational field outside a perfectly spherical, non-rotating mass.
Wow.
It's just a testament to the human spirit that he completed this groundbreaking paper just weeks before his tragic death from a rare autoimmune disease contracted during his service.
What an incredible, almost heartbreaking backdrop to such a fundamental discovery. So this solution, born out of such challenging circumstances, what exactly did it describe, and why did it become so foundational for our understanding of black holes?
Well, initially, Schwarzschild's work was largely considered a mere theoretical exercise. Its profound implications for something as extreme as a black hole weren't widely recognized for decades.
People didn't quite get it yet.
The scientific community had to slowly catch up to the mathematics.
Yeah.
However, its true meaning was gradually revealed through the persistent efforts of brilliant scientists working on stellar evolution, like Subrahmanyan Chandrasekhar.
Who calculated the limit for white dwarfs, right?
Exactly. And J. Robert Oppenheimer, renowned for his role in the Manhattan Project.
Mm-hmm.
In 1939, Oppenheimer, along with his student Hartland S. Snyder, expanded upon Schwarzschild's framework, proposing the theoretical existence of gravitationally collapsed stars, essentially.
Yeah.
The first modern concept of a black hole. They described how incredibly massive stars might indeed collapse into such objects.
So that was the theoretical birth, really.
Pretty much. Today, the Schwarzschild solution is recognized as the definitive description of a static black hole, a cosmic entity characterized solely by its mass, possessing neither electrical charge nor rotation. It's often referred to as a cosmic laboratory.
Why laboratory?
because its simplicity allows physicists to study fundamental gravitational properties without the added complexities of spin or charge. It isolates the effect of pure mass on spacetime.
And what this tells us, connecting it to the bigger picture, is truly remarkable. How a purely theoretical concept, initially dismissed as an abstraction, became absolutely central to our understanding of the universe.
Precisely. It became integral to understanding the ultimate fates of massive stars, the intricate processes of galaxy formation and evolution, and perhaps most crucially, as these unique physical laboratories where the laws of physics can be tested at their most extreme limits.
Amazing.
This journey, from a wartime mathematical calculation to a cornerstone of modern astrophysics, powerfully underscores the transformative potential of theoretical insight. It shows us how abstract mathematics can, with time and deeper understanding, unveil profound truths about the universe we inhabit.
Now, this is where things get really fascinating, as we peel back the layers to explore the fundamental components of a black hole from a classical perspective. At its heart, a black hole is simply a region in space-time where an immense amount of mass is compressed into an incredibly tiny volume.
Unimaginably dense.
This compression creates such an intense gravitational pull that nothing, not even light itself, can escape its clutches. It truly is the ultimate cosmic trap, and this structure is defined by two primary and profoundly counterintuitive components, the singularity and the event horizon.
And these are indeed critical, mind-bending distinctions. The singularity is the central point of a black hole, an infinitely small region where all of its mass is concentrated, leading to, well, infinite density.
Infinite? How is that even possible?
That's the classical prediction. What's crucial to grasp here is that at this vanishingly small point, the laws of physics as we currently understand them completely break down.
They just stop working.
They stop making sense. Our equations go to infinity. This breakdown represents a profound open problem in modern physics, a frontier where our current theories are simply inadequate. It screams for new physics, perhaps a unified theory of quantum gravity, to fully describe what happens at such extreme, unprecedented conditions.
Infinitely small, infinitely dense, that's a concept that really stretches the imagination to its absolute limit. And then we have the event horizon.
Right. The event horizon, in contrast to the singularity, is an imaginary non-physical sphere surrounding it. It represents the ultimate point of no return.
The edge.
Exactly. At this boundary, the escape velocity, the speed an object needs to travel to break free from the black hole's gravity, becomes precisely equal to the speed of light.
Ah, the cosmic speed limit.
Precisely. Since nothing can travel faster than light, anything, including light itself, that crosses this boundary is irrevocably trapped. The radius of this sphere, by the way, is known as the Schwarzschild radius, a direct and crucial consequence of Karl Schwarzschild's groundbreaking solution.
So imagine you were falling into a black hole and crossed that event horizon. What would it actually feel like? Would you be torn apart immediately, or is it subtle?
Well, this is where it gets really intriguing. According to General Relativity, an observer falling toward a static black hole would feel absolutely nothing unusual as they cross the event horizon.
Nothing at all. No big jolt?
Nope. There's no physical barrier, no sudden jolt, no dramatic force pulling at you at that precise moment. It's a purely mathematical boundary defined by the escape velocity.
Okay.
However, for a distant observer, someone watching you fall in from far away, the situation would appear profoundly different.
How so?
From their perspective, your clock would appear to slow down dramatically as you approach the event horizon. It would get slower and slower,
Yeah.
eventually seeming to freeze right at the boundary itself.
So I'd look frozen in time to them.
Exactly. This is due to extreme relativistic time dilation, a consequence of space-time being so severely warped near the black hole. You would essentially appear to be stuck in time, forever hovering just outside the point of no return, never quite reaching it from their vantage point.
Wow. Two completely different realities playing out simultaneously. It really makes you think about the nature of observation, doesn't it?
Absolutely. It's a testament to the mind-bending power of Einstein's theory.
Now, you mentioned something earlier about black holes possessing a surprising simplicity. That seems profoundly counterintuitive for such extreme and mysterious objects. How can something so complex be simple?
It does seem contradictory, doesn't it?
Yeah.
And this brings us to a fundamental principle known as the no-hair theorem, or sometimes the black hole uniqueness theorem.
No hair.
Okay. The profound insight here is that this theorem suggests that all stationary black holes, ones that have settled down, can be completely and uniquely characterized by just three externally observable parameters.
Wow.
Their mass, m, their angular momentum or spin,
Sure.
J, and their electric charge, Q.
Mass, spin, charge. That's it.
That's it, according to the theorem.
No hair. What does that metaphor actually mean? Are black holes just bald in some cosmic sense?
Last slightly. Yeah, kind of. The hair metaphor refers to any other information or properties about the matter that originally formed the black hole or has since fallen into it.
Like what kind of star it was, or what fell in later.
Exactly. The theorem posits that all such information, whether it's a star made primarily of hydrogen or helium, what its specific temperature or magnetic field was, or even a type of matter that contributed to its growth, all of that hair is effectively smoothed out and disappears behind the event horizon. It's permanently lost to the outside universe. So regardless of how complex or unique the matter that collapsed to form it, once it's a stable black hole, it effectively forgets its past, retaining only those three fundamental properties: mass, spin, and charge. It's like throwing all your old unique clothes into a black box, and when you shake it, only a generic identical cube comes out no matter what you put in.
So it's essentially a statement about information being lost forever behind that horizon.
Precisely. The initial version of this theorem, for the simplified case of the non-rotating, uncharged Schwarzschild black hole, was rigorously proven by Werner Israel back in 1967. This was a landmark result, establishing that if a static black hole solution existed, its geometry had to be uniquely determined by its mass alone.
But it's more complicated for rotating or charged ones.
Yes. While the theorem is widely accepted by physicists for its profound elegance and explanatory power, a complete, rigorous mathematical proof for all cases, particularly for the more general Kerr-Newman metric, which describes rotating and charged black holes, remains a significant mathematical challenge. This is why some mathematicians still refer to it as the no-hair conjecture. Still work to be done there.
And this leads us directly to a monumental conflict, doesn't it? If information is truly lost behind the event horizon, doesn't that directly contradict one of the most fundamental principles in all of physics?
It absolutely does, and this is where the no-hair theorem establishes a profound and deeply unsettling tension. Its premise of information loss directly contradicts a fundamental law of quantum mechanics known as unitarity.
Unitarity, meaning information can't be destroyed.
Right. Quantum mechanics dictates that information can never be truly destroyed, only transformed or rearranged. This conflict is central to what's known as the black hole information paradox, which we'll definitely dive into later. It sets up one of the most significant theoretical battles in modern physics. And what's even more compelling is that the results of the first gravitational wave observations in 2015, which we'll discuss shortly, were remarkably consistent with the predictions of the no-hair theorem. They saw black holes merge, and the resulting black holes seemed to fit the mass-spin charge description perfectly.
So observations actually back up this information-losing idea.
They seem to, yes. This observational validation further sharpens this already potent theoretical tension, pushing us to the very edge of our understanding. It's a real head-scratcher.
So if we step back for a moment and consider the universe as a whole, what does all this mean? It turns out black holes aren't just a single monolithic entity. They're actually a diverse class of cosmic objects, almost like a cosmic menagerie, distinguished primarily by their mass and the ways they form.
Indeed. It's a whole spectrum, ranging from the theoretically minuscule to the absolutely gargantuan, each with its own origin story.
Okay, break it down for us. What are the main types?
First, we have stellar mass black holes. These are the most common type we know of, formed from the dramatic gravitational collapse of truly massive stars, those significantly larger than our sun at the very end of their lives.
Born from dead stars.
Exactly. They typically have masses ranging from about 5 to several tens of solar masses, maybe up to around 100 times the mass of our sun. While the black holes themselves are invisible, we detect them indirectly. Often, they're part of a binary system, orbiting another star.
Stealing gas from their neighbor.
As pretty much. As they accrete matter from their companion, that gas gets superheated by friction to extreme temperatures, emitting intense X-rays, which gives away their presence. We also detect them through gravitational waves from their mergers, as we'll soon explore. That's become a huge new way to find them.
So those are born from dying stars. Is there a middle ground in terms of size, something between stellar and, well, the really big ones?
Yes. The next class is intermediate mass black holes, or IMBHs. These represent a theoretical gap in our understanding, or at least they used to be more theoretical. Their mass range is roughly from hundreds to hundreds of thousands of solar masses.
So much bigger than stellar, but not galaxy center big.
Right. Their formation mechanisms are a bit of a mystery, making them one of the universe's more elusive puzzles. How do you get something that big, but not super big? We've identified a few promising candidates, typically found in the centers of dwarf galaxies or within very dense star clusters, but their existence is harder to nail down, and their origins are still hotly debated.
And then the true behemoths, the giants that anchor entire galaxies.
Absolutely, the supermassive black holes, or SMBHs, these are the colossal entities found at the centers of most large galaxies, including our own Milky Way's Sagittarius A.
SGRA.
Their masses are truly extraordinary, ranging from hundreds of thousands to billions with a B of solar masses. Their presence is a defining feature of what we call active galactic nuclei, or AGNs, and quasars.
Quasars, those incredibly bright things.
Exactly. In these systems, vast amounts of infalling matter create some of the brightest and most energetic phenomena in the entire universe, often outshining their entire host galaxy. Billions of stars worth of light coming from just the region around the black hole.
And what about the ones that might have formed even earlier, in the universe's infancy, before stars even had a chance to die? Are there relics from the Big Bang?
That's the idea behind primordial black holes. This is a hypothetical class theorized to have formed in the very early universe, shortly after the Big Bang. Not from stellar collapse, but maybe from density fluctuations.
So they could be tiny or huge.
Theoretically, yes. They could have a wide range of masses, from microscopic, perhaps the size of an atom carrying the mass of a mountain, up to much larger, even supermassive sizes, formed directly in the primordial soup. We haven't definitively observed them yet, but if they exist, they could be detectable through unique gravitational wave signatures, or maybe through lensing effects. Finding them would offer a truly unique window into the very first moments of cosmic existence.
It's incredible how diverse these objects are, suggesting many different paths to their formation. But you mentioned an intriguing theoretical gap earlier, an absence of certain stellar black holes. Can you elaborate on that? Because it sets up a really interesting puzzle.
Yes, and this upper mass gap is a crucial point that will connect directly to later observational breakthroughs we'll talk about. Standard stellar evolution models predict a significant absence of stellar black holes within the range of approximately 50 to 150 solar mass.
The forbidden zone.
Kind of. And what's particularly compelling here is that this isn't just an arbitrary boundary. It's predicted as a direct consequence of a specific, incredibly violent stellar phenomenon known as pair instability supernovae.
Pair instability supernovae. That sounds incredibly dramatic. What exactly happens there?
They are indeed amongst the most energetic events in the universe. According to the theory, extremely massive stars in this specific mass range, typically those with initial masses between, say, 130 and 250 solar masses, experience a unique instability right at the end of their lives.
What kind of instability?
In their core, high-energy gamma rays become so energetic they start spontaneously producing electron-positron pairs. This process effectively siphons off energy that would normally provide the outward radiation pressure supporting the star against its own immense gravity.
So the support just vanishes.
Pretty much. With this crucial support diminished, the core rapidly contracts, triggering a runaway thermonuclear explosion so powerful that it completely blows the star apart, utterly disintegrates it.
Wow. And what's left?
Nothing. That's the crucial point. It leaves absolutely no stellar remnant behind, no black hole, no neutron star. The star effectively vanishes in a glorious destructive flash of light. Obliterated.
So because of this, our models predicted that black holes simply shouldn't exist in that 50 to 150 solar mass range because the stars that might form them just blow themselves up completely.
Exactly. This prediction was a cornerstone of our understanding of stellar death, and it was considered a very robust theoretical boundary for the maximum mass a black hole could attain from a single stellar collapse. It sets the stage for a dramatic contradiction that would later emerge from gravitational wave astronomy.
Oh, I see where this is going.
Yeah, a thrilling scientific puzzle that fundamentally reshape our understanding of black hole formation, and one we'll definitely revisit shortly. It's a great example of theory making a prediction and then observation coming along to shake things up.
All right, let's turn our attention to the sheer drama of how black holes are actually born. For stellar mass black holes, this is actually a pretty well understood endpoint in the life cycle of a massive star. Most of a star's existence is spent in this delicate cosmic ballet called hydrostatic equilibrium.
The balance.
Right, where the immense outward thermal pressure generated by nuclear fusion in its core is perfectly balanced by the relentless inward pull of its own gravity. It just sits there, burning away. But what happens when that fusion engine runs out of fuel?
When the fusion processes cease, gravity inevitably takes over. There's nothing left to push outwards. Without that powerful outward pressure, the stellar core rapidly contracts under its own immense weight. The ultimate fate of that collapsing core depends critically on its precise mass.
Okay, so mass is key. What are the options?
If the core mass is below the Chandrasekhar limit, which is about 1.44 times the mass of our Sun, the collapse is dramatically halted by electron degeneracy pressure.
Quantum mechanics steps in.
Exactly. It's a powerful quantum mechanical effect. Essentially, electrons pushing back against further compression because they can't occupy the same quantum state. The result is a white dwarf, a super-dense remnant composed mostly of carbon and oxygen, about the size of the Earth, but with the mass of the Sun. It will eventually cool over trillions of years to become a theoretical black dwarf.
But what if it's heavier than that limit? What then? Does it keep collapsing?
For more massive stellar cores, specifically those with masses between the Chandrasekhar limit and another critical threshold, the Tolman-Oppenheimer-Volkoff, or TOV, limit, the gravitational pressure becomes so immense that electrons and protons are literally forced to combine, forming neutrons.
Squeezed together.
Yeah, it's called neutronization. This results in an even denser, incredibly compact object, the neutron star. Here, the collapse is halted by an even stronger quantum force, neutron degeneracy pressure, plus powerful short-range repulsive nuclear forces between the neutrons themselves. Think of the mass of the Sun crammed into a sphere maybe the size of a city.
Unbelievably dense. And if the core is even more massive than the TOV limit, is there anything left to stop it then?
If the mass of the stellar remnant exceeds the TOV limit, which is currently estimated to be somewhere in the range of 2.01 to maybe 2.17 solar masses, the exact value is still debated and depends on the nuclear equation of state.
So roughly twice the mass of the Sun or a bit more.
Right. If the collapsing core is heavier than that, then there is truly no known force in the universe capable of counteracting the overwhelming power of gravity. The core collapses indefinitely, crushing itself towards an infinitesimally small point, the singularity.
Total gravitational victory.
Exactly. As the escape velocity from its surface reaches the speed of light, an event horizon forms, and that, my friend, is precisely how a stellar mass black hole is born.
It just keeps collapsing forever.
According to classical GR, yes. It's also an intriguing theoretical possibility that some extremely massive stars might collapse directly into a black hole without a huge supernova explosion, an event sometimes dubbed an unnova.
In an unnova, it just vanishes.
In such a scenario, the star would simply appear to vanish from the sky without the usual bright flash. Just the sudden disappearance as it collapses past its own event horizon. We might have even seen hints of this happening.
What's fascinating here is how the scientific understanding of this crucial TOV limit has evolved over time. You mentioned the range is still being refined. It really illustrates the symbiotic relationship between theoretical work and observational science, doesn't it?
Indeed. It's a great example. The original calculation by Oppenheimer and Volkoff back in 1939, based on a fairly simple idealized model of neutrons, placed the limit as a surprisingly low value of only 0.7 solar masses.
Way too low. We see neutron stars much heavier than that.
Exactly. This low value was later directly contradicted by the discovery of actual neutron stars with masses well over 2 solar masses. This forced physicists to refine their theoretical models to account for more complex factors like the strong nuclear force interactions between neutrons and potentially rapid rotation, which can help support the star.
So the models got better because of observations?
Right. And more recently, if we connect this to the bigger picture, data from the gravitational wave signal, GW17 a day 817, that famous neutron star merger event.
Ah, yes, the kilonova.
That one. The signal from the merger and what happened afterwards as it likely collapsed into a black hole provided a new, independent, and incredibly precise measurement that constrained the TOV limit to a much tighter range, closer to that 2.1-ish solar mass value.
Wow, gravitational waves helping pin down nuclear physics.
Exactly. This ongoing refinement of a fundamental physical limit beautifully demonstrates the iterative and self-correcting nature of the scientific process, where observations continually push theory to greater accuracy and understanding.
So that explains how stellar mass black holes form from massive stars. But what about the truly gargantuan ones? The supermassive black holes at the centers of galaxies. How do they get so incredibly big? Millions or billions of solar masses.
That is precisely the central and unsolved problem in cosmology. Seriously, it's a huge question. Standard models of stellar collapse simply cannot account for the sheer astronomical mass of these objects.
They can't just be collections of stellar black holes.
Not easily. especially not that early in the universe. What's more, observations have revealed that these SMBHs were already in place very early in cosmic history, within the first billion years after the Big Bang. We see quasars powered by billion solar mass black holes when the universe was less than 10% of its current age.
That seems far too early for them to have grown to their enormous size solely from stellar mass seeds via typical gradual accretion processes, right? Like eating gas one bit at a time.
Exactly. This time paradox poses a huge challenge to our current models. They needed to grow incredibly fast or start much bigger.
So if they can't just grow from regular stellar mass black holes easily, how do we explain their existence so early in cosmic history? What are the leading ideas?
There are two main theoretical models proposed to explain their origin, broadly categorized as light and heavy seeds.
Okay, light seeds first. What's that about?
The light seed model suggests that SMBHs grew from the remnants of the universe's very first stars, known as population 3 stars. These were thought to be very massive, maybe 100 solar masses or so, made of pure hydrogen and helium. So the initial seeds would have started with masses of around 100 solar masses.
Still pretty small compared to a billion.
Very small. The primary challenge with this model is the incredibly short timescale required for these seeds to accrete enough mass, billions of solar masses worth, to power the high redshift quasars we observe today. Light seeds are thought to accrete gas at rates maybe close to, or even below, the theoretical maximum known as the Eddington limit. Plus, they might be in environments where gas isn't super abundant, so getting them to grow that fast is a significant hurdle.
So they just can't grow fast enough to explain those early massive quasars easily?
Not easily, no. It requires some very specific conditions, maybe super Eddington accretion bursts, but it's tough. Alternatively, the heavy seed model proposes the formation of direct collapse black holes, or DCBHs.
Direct collapse, skipping the star part.
Exactly. In this scenario, massive primordial gas clouds, under very specific and rare environmental conditions, collapse directly into a black hole without forming a star first. These black holes would start with a much larger initial mass, typically around 100,000 solar masses.
Okay, 100,000 is a much better starting point than 100.
Absolutely. That would more readily account for the presence of those overmassive black holes observed in the early universe. It gives them a huge head start.
But you said specific and very rare environmental conditions. What does that mean?
The key here is you need conditions that prevent the gas cloud from fragmenting and forming normal stars as it collapses. This seems to require metal-free gas, which cools less efficiently than gas enriched with heavier elements, and crucially, a very strong background of ultraviolet radiation, specifically Lyman-Werner photons.
Why the UV light?
These high-energy photons can break apart molecular hydrogen, H2, which is the main coolant in primordial gas clouds that allows them to fragment into stars. So if you have a strong enough UV bath, it essentially sterilizes the gas, destroying the H2, preventing normal star formation, and allowing a much larger, pristine gas cloud to collapse monolithically under its own gravity directly into a massive black hole seed.
Wow, so you need just the right cosmic neighborhood.
Precisely. While these heavy seeds offer a compelling explanation for the existence of high redshift quasars, the presumed rarity of these perfect conditions makes their overall prevalence in the early universe a topic of ongoing research and debate. Maybe both light and heavy seeds play a role. It's still an active area.
It's clear that understanding these different formation pathways is a central quest, highlighting the ongoing scientific effort to explain the universe's grandest structures. Now, for the truly mind-bending part, since black holes are, by definition, invisible, how on Earth do we see them? Astronomers must be incredibly clever.
They absolutely are. It takes some serious ingenuity. We can't directly image the black hole itself, as it emits no light of its own. But we can detect its presence through its profound and often violent effects on its surroundings. We employ two main approaches: indirect inference, observing the drama around them, and now groundbreaking direct observation, capturing their shadowy silhouettes.
It's like finding a trail of crumbs that tells you someone was there, even if you don't see them directly, like seeing ripples in water.
Exactly, a perfect analogy. One of the primary indirect signatures is the existence of an accretion disk. This is a swirling disk of plasma and gas that falls toward the black hole, drawn in by its immense gravity like water swirling down a drain.
But much, much hotter.
Oh yes. As the matter in this disk spirals inwards, jostling against itself, intense friction heats it to hundreds of millions, even billions of degrees. This causes it to emit intense radiation, often across the electromagnetic spectrum, but most powerfully in the X-ray range.
Wow.
That's a dead giveaway.
And that's what powers quasars.
Precisely. In extreme cases, this superheated, rapidly infalling matter creates a quasar, which, as we said, is one of the brightest and most energetic objects in the entire universe, a cosmic lighthouse powered by the hungry supermassive black hole at its heart.
And I've heard about gravitational lensing where light gets bent. How does that help us detect something we can't see?
Gravitational lensing is another powerful observational tool. The immense gravity of a black hole, or any massive object really, warps spacetime around it, and this warped spacetime bends the path of light rays from a background source that pass nearby. It acts like a cosmic magnifying glass or lens.
So you see distorted images of things behind it?
Sometimes, yes,
Yeah.
or multiple images, or just a brightening.
Yeah.
But what's truly ingenious is how astronomers have harnessed a specific type of lensing called gravitational microlensing. This involves the brief brightening of a background star, or quasar, as a foreground object. Maybe a star, planet, or even an isolated black hole passes almost directly in front of it from our line of sight.
And Hubble used this.
Yes, the Hubble Space Telescope employed this technique in a really clever way to scan across the accretion disk of a distant quasar. As foreground stars in the quasar's host galaxy moved, their microlensing effects magnified different parts of the background accretion disk at different times.
This is where it gets incredibly insightful. What kind of detail could they actually get from that? That sounds amazing.
This incredible precision allowed astronomers not just to estimate the overall size of the disk, which is a significant feat in itself, but even to map out its temperature profile. They could confirm that the disk becomes progressively bluer and hotter the closer it is to the central black hole, just as theory predicts.
Wow.
This was a remarkable achievement, obtaining observational data on the internal structure of these systems for the first time, moving beyond purely theoretical models to actual measurements of these exotic environments. It's a true aha moment, transforming a theoretical concept like an accretion disk into a directly observed, measurable cosmic furnace.
That's truly ingenious. But the most dramatic form of black hole detection has to be something else entirely, right? Something that lets us hear the universe, in a way.
Indeed, the most dramatic and arguably most groundbreaking direct detection came with the observation of gravitational waves, those elusive ripples in the very fabric of space-time, predicted by Einstein's theory of general relativity a century earlier, but never directly seen until recently.
LIGO.
Exactly. The first ever direct detection was made by the Laser Interferometer Gravitational Wave Observatory, or LIGO, back in 2015. It captured the fleeting chirp signal from the catastrophic merger of two stellar mass black holes spiraling into each other. A monumental moment in scientific history that opened a whole new window onto the cosmos. Gravitational wave astronomy was born.
And there was a much more recent detection that really shook things up and challenged our models, wasn't there? The one that hit that mass gap.
This is where things get really intriguing.
Yep.
Yes, a particularly notable recent discovery is the detection of GW231123. This was announced as the most massive black hole merger ever observed with gravitational waves by the LIGO Virgo K-GRA collaboration.
How massive are we talking?
This event resulted from the coalescence of two pretty hefty black holes, one estimated at approximately 100 times the mass of the Sun and the other around 140 times the mass of the Sun. They merged to form a final, even larger black hole of roughly 225 solar masses.
Wait a second. Okay, rewind. Didn't you mention earlier that there was that forbidden upper mass gap for stellar mass black holes, roughly between 50 and 150 solar masses because of those pair instability supernovae?
I did indeed.
That 100 and 140 solar mass black hole discovery seems to fly right in the face of that. They're smack bang in the middle of the forbidden zone. How do we reconcile that contradiction?
You're absolutely right to make that crucial connection. This observation presents a significant challenge, maybe even overturns part of our prior astrophysical models of black hole formation. The existence of black holes with masses of 100 and 140 solar masses places them directly in that upper mass gap, a range previously considered forbidden, or at least very sparsely populated, by standard stellar evolution models because of that pair instability supernova mechanism. It's a thrilling scientific puzzle.
So how do we resolve this? What does this mean for our understanding of how black holes actually form? Did the supernova theory get it wrong?
Well, maybe not entirely wrong, but incomplete. This raises an important question, and it's led to a significant shift in thinking. The observation of black holes in this forbidden mass range has significantly increased confidence in the hierarchical merger hypothesis.
Hierarchical merger, meaning black holes merging with other black holes.
Exactly. This theory posits that black holes can form not only from the collapse of a single massive star, but also from the merger of two or more smaller black holes. Essentially, two black holes merge to form a larger one, perhaps putting it into the mass gap, and then maybe that new larger black hole can merge with another one later, building up even larger masses that sidestep the limitations of the pair instability gap for single stars.
So they can be second generation or third generation black holes?
Precisely. This finding fundamentally reshapes our understanding of how black hole populations are formed and evolve, suggesting a more dynamic, multi-generational process than previously assumed. It's a powerful demonstration of how observation continually refines and sometimes completely overturns our theoretical understanding. Nature found another way.
That's a huge shift in our understanding of black hole evolution. Incredible. And then, of course, there's the most iconic visual evidence for black holes, the actual pictures, so to speak, that brought them into popular imagination in a way nothing else had.
Yes, the Event Horizon Telescope, or EHT, has delivered truly iconic visual evidence. This isn't a single telescope, but an amazing array that links radio observatories across the globe, from Hawaii to Chile, Spain to the South Pole, to form a single Earth-sized virtual telescope.
An Earth-sized telescope.
Effectively, yes. This technique, known as Very Long Baseline Interferometry, or VLBI, provides an unparalleled level of angular resolution, the ability to see fine detail. They often use the analogy of being able to discern a tennis ball on the surface of the moon. That's the kind of precision required to image something like the event horizon of a black hole, which is incredibly distant and actually quite small in the sky, even for supermassive ones.
I remember seeing those stunning images. The first one in 2019 was of M87, the giant in the Messier 87 galaxy, right? That orange donut.
Correct. The EHT collaboration produced that first groundbreaking image of a black hole shadow in 2019, revealing the supermassive black hole at the center of the galaxy Messier 87, designated M87. A subsequent equally iconic image was released in 2022, this time of Sagittarius A, or SGRA, the supermassive black hole at the very center of our own Milky Way galaxy.
Which looked kind of similar, but maybe a bit fuzzier.
A bit, yeah. SGRA is much less active, and the gas around it is more dynamic, making it harder to image. But still, an incredible achievement.
And it's crucial to clarify that we're not actually seeing the black hole itself, because it's truly black, right? It's not like a star shining. What are we seeing in those images?
Precisely. It's vital to understand that these images do not show the black hole itself, as it emits no light. Instead, they show a central dark region, the shadow, that is silhouetted against the incredibly bright, superheated light emitted by the gas in its surrounding accretion disk.
So the shadow is the region where light can't escape, outlined by the glowing gas. Essentially, yes. The images provide direct visual evidence of light being bent and captured by the extreme gravity of the black hole. The bright, ring-like structure reveals light from the accretion disk that's been bent and focused by the powerful gravitational field, warping around the black hole's silhouette, just as Einstein's General Relativity predicted over a century ago. Connecting this to the bigger picture, it's a powerful and visually stunning confirmation of GR in the strong field regime and an incredible testament to human ingenuity and international scientific collaboration. Seeing is believing, in a sense.
So, what does this all mean for the grand scheme of the universe? We've talked about individual black holes and their formation, their anatomy, but now let's zoom out to their grander role. Supermassive black holes aren't just passive residents sitting at galactic centers, they're active architects, profoundly influencing the large-scale structure of the universe and the evolution of entire galaxies. This isn't a passive relationship, is it? It's more like a profound, active, co-evolutionary dance between a supermassive black hole and its host galaxy. That's a perfect way to characterize it. It's definitely not a passive relationship. There's a strong and long-standing correlation observed between the properties of supermassive black holes and their host galaxies.
Like bigger galaxies have bigger black holes.
Exactly. For instance, a larger, more massive galactic bulge, the central part of the galaxy typically harbors a more massive black hole. And there's a specific empirical relationship, quite tight actually, between the black hole's mass and mutation and the galaxy's velocity dispersion.
Velocity dispersion. That's how fast the stars are moving around randomly in the bulge.
Basically, yes. It measures how stirred up or dynamically hot the stars are, which is related to the depth of the galaxy's gravitational well. This correlation, the M-sigma relation, suggests a fundamental causal link. It implies they have somehow co-evolved and influenced each other's growth over cosmic history. This connection is particularly important in explaining how the central mass of a black hole seems to be a key factor in determining the final properties of its surrounding galactic bulge, even though the black hole itself is tiny compared to the galaxy.
So how does this coevolution actually work? What are the specific mechanisms by which a black hole, which is relatively minuscule compared to its entire galaxy, can have such a profound and far-reaching influence on star formation billions of light years away from it?
This is where the concept of AGN feedback comes in. It's become a cornerstone of galaxy evolution models. The profound insight here is that AGN feedback is the process where the immense energy released by a growing supermassive black hole, an active galactic nucleus, or AGN, influences the multi-phase gas, meaning gas existing at different temperatures and densities throughout its host galaxy.
So the black hole eating gas affects the rest of the galaxy's gas.
Exactly. This feedback can occur in two distinct modes, often linked to how fast the black hole is accreting matter, creating a powerful, dynamic, self-regulatory loop that governs the growth of both the black hole and the galaxy. It keeps things in check.
Okay, let's break that down. Let's start with negative feedback. How does that suppress star formation, and why is that important for galaxy evolution?
When a supermassive black hole accretes gas at a very high rate, close to its maximum capacity, it enters what we call a quasar mode, or radiative mode. During this phase, it shines incredibly brightly and releases immense energy in the form of powerful radiation pressure outflows and winds that blast out from the galactic center at high speeds.
Like a galactic superwind.
Pretty much. These outflows can be powerful enough to either completely eject gas from the galaxy's potential, well, sending it out into intergalactic space, or heat the gas remaining within the galaxy to such high temperatures that it simply cannot cool down and collapse gravitationally to form new stars.
So it shuts down the star factory.
Exactly. By quenching star formation, this negative feedback process helps reproduce the observed bimodal distribution of galaxy colors. We see blue, star-forming spiral galaxies, and red, non-star-forming elliptical galaxies. This feedback helps explain why massive, early-type galaxies become red and dead, meaning they've largely stopped forming stars and cluster around what we call the red sequence in galaxy color magnitude diagrams.
Does it solve any other problems?
Yes. Critically, this feedback also helps solve a major theoretical puzzle known as the overcooling problem. Early simulations without AGN feedback predicted that gas in massive dark matter halos should cool very efficiently, leading to galaxies forming far too many stars and becoming much more massive and luminous than what we actually observe today.
So the feedback stops them getting too big.
Precisely. This negative feedback mechanism acts as a kind of cosmic thermostat, fine-tuning galactic evolution and ensuring galaxies don't grow runaway large too quickly. It regulates things.
That makes perfect sense for suppressing star formation. But can there also be positive feedback where the black hole actually triggers star formation instead of stopping it? That seems completely counterintuitive. How can blowing stuff out make more stars?
It does sound odd, but yes, absolutely. This seems to occur more often at lower accretion rates during what we often call the radio mode or jet mode of feedback.
Radio mode, like those big radio jets we see.
Exactly. In this mode, the AGN might not be shining as brightly overall, but it drives powerful, collimated jets of relativistic plasma and expands massive radio lobes or cocoons, huge bubbles of hot plasma inflated by the jets into the interstellar medium of the host galaxy.
Okay, so jets instead of winds. How does that trigger stars?
Well, numerical simulations have shown that the enhanced pressure from these expanding jets and cocoons can sweep up and compress the ambient gas in the galactic disk or halo. This compression can create shock waves that accelerate the formation of dense molecular clouds.
Ah, and molecular clouds are where stars are born.
Precisely. They are the stellar nurseries. So by compressing the gas and triggering the formation of these clouds, the AGN jets can actually induce new bursts of star formation in specific regions of the galaxy, even while potentially clearing gas out elsewhere. It's a more complex picture.
So what does this all mean for the big picture of galaxies? It sounds like a complex, delicate, and deeply intertwined dance between a black hole and its host galaxy over billions of years.
It's a truly dynamic, self-regulatory system. Think of it as a grand cosmic cycle playing out over and over. Maybe a phase of intense star formation or a galaxy merger funnels large amounts of gas to the galactic center. This fuel ignites the black hole, triggering a phase of high accretion quasar mode feedback.
Which blows out the gas.
Right. This powerful negative feedback then expels or heats the gas, effectively quenching further star formation nearby and maybe starving the black hole itself of new fuel.
So it shuts itself off.
Temporarily. As the black hole's accretion rate drops, it might shift to a lower power radio mode. The jets from this mode can then perhaps compress existing gas further out in the galaxy, triggering new cycles of star formation elsewhere.
A feedback loop.
Exactly. This powerful causal loop, cycling between positive and negative feedback depending on the accretion rate and environment, is the leading explanation for the observed correlation between black hole mass and galaxy properties like the M-sigma relation. It provides a mechanism for regulating galactic growth and star formation activity over cosmic time. It's really an elegant solution to a massive cosmic puzzle. How do tiny black holes talk to huge galaxies? Through feedback.
All right, let's now journey to the ultimate frontier, where physics itself seems to break down. This is heavy stuff. We're transitioning now to one of the most profound, unresolved debates in physics, stemming from the fundamental clash between Albert Einstein's general theory of relativity, which describes gravity and the very large, and quantum mechanics, which describes the very small, particles and forces. The black hole information paradox is a classic, captivating example of this deep-seated conflict.
This paradox truly highlights the deep chasm that exists between our two most successful physical theories. They work perfectly well in their own domains, but when you try to apply both to a black hole, especially its event horizon and singularity, they give contradictory answers. The problem really came into sharp focus with Stephen Hawking's groundbreaking 1974 discovery.
Hawking radiation.
Exactly. He applied quantum field theory concepts to the curved space-time around a black hole's event horizon and found something astonishing. Black holes aren't truly black. They actually radiate particles, photons, neutrinos, etc., as if they were a hot object, a black body, with a specific temperature inversely proportional to their mass.
So smaller black holes are hotter.
Yes, much hotter. This phenomena, known as Hawking radiation, slowly drains energy, and thus mass, via EMC from the black hole, and causes it to evaporate over immense, truly astronomical timescales for stellar mass or larger ones. But eventually, theoretically, they shrink until they vanish completely.
So black holes aren't eternal cosmic prisons. They shrink and eventually disappear. That's a mind-blower itself.
Precisely. And this is where the paradox lies. According to Hawking's original calculations, this radiation is predicted to be purely thermal and random. Think of the random hiss of static from heat. It means it carries no information about the specific matter that fell into the black hole to form it or feed it over its lifetime.
No information at all.
That was the initial calculation. To illustrate, imagine you threw a unique, exquisitely detailed book full of profound insights and specific quantum states encoded in its atoms into a black hole.
My prized first edition.
Chuckles. Exactly. According to Hawking's initial calculations, all that information, the quantum states of the particles that make it up, the specific arrangement of atoms that convey the text, everything that made that book unique would seemingly be utterly destroyed when the black hole eventually evaporates into this random, information-free Hawking radiation.
Forever.
This directly violates one of the most fundamental principles of quantum mechanics: unitarity. Unitarity essentially dictates that information is always preserved. It can be scrambled, hidden, transformed, but never truly destroyed. It's as if you burned your prized book, but the smoke and ashes, if you could analyze them perfectly, would still contain all the information needed to reconstruct the original book, at least in principle. Hawking radiation seemed to say no. The information just vanishes.
So one of our fundamental theories, general relativity, leading to black holes and Hawking radiation, says information is lost. And the other fundamental theory, quantum mechanics, says information must be preserved. That's a direct, undeniable conflict and a truly mind-bending problem. What kind of radical ideas have emerged from physicists trying to solve this? There must be some wild theories.
Oh, absolutely. This information paradox has indeed led to several radical theoretical proposals, each of which attempts to resolve the conflict by fundamentally re-examining the nature of black holes, space-time, and information itself. One such idea, emerging from string theory, is the fuzzball hypothesis.
Fuzzball. Okay, intriguing name.
It proposes a radical alternative to the classical picture we've been discussing. In the fuzzball scenario, black holes are not a singularity surrounded by a smooth, empty event horizon where spacetime is classical. Instead, a black hole is envisioned as a fuzzball, a massive, incredibly dense and messy quantum-bound state of fundamental strings and brains, with no classical event horizon and no singularity in the usual sense.
A fuzzball, so no infinitely small point and no sharp event horizon that you just fall through. It's like a giant quantum object.
Exactly. In this model, the black hole structure extends all the way out to roughly the location of the classical event horizon. But it's a quantum fuzzy boundary, not an empty space boundary. An infalling object never reaches a singularity because there isn't one. It simply interacts with and gets entangled with the strings making up the fuzzball state. Its information becomes part of the fuzzball's complex quantum state, preserved on this extended surface. Imagine it less like a solid, smooth marble, and more like a colossal ball of incredibly intricate yarn, where every strand represents a fundamental string configuration. Anything that touches it just becomes woven into that ever-growing, ever-entangled structure.
So information isn't lost, it's just incorporated into the fuzzball state.
That's the idea. The fuzzball theory resolves the paradox by eliminating the classical event horizon and singularity altogether, thereby preserving information encoded in the quantum state of the fuzzball itself, which could then, in principle, be radiated away as the fuzzball evaporates.
That sounds like an elegant solution from string theory, but I imagine there are counterarguments and other radical ideas from different perspectives.
There certainly are. The fuzzball picture is compelling, but still under development and faces its own challenges. In response, partly to questions about what happens right at the horizon, the firewall paradox emerged around 2012 from work by Harry, Moralf, Polchinski, and Sully, AMPS.
Firewall. That sounds dramatic.
It is. This argument suggests that if you demand that quantum mechanics, specifically principles related to entanglement, holds true for the Hawking radiation emitted by an old black hole, then something drastic must happen at the event horizon. To preserve quantum entanglement and solve the information paradox, they argued, a high-energy firewall would have to exist right at the event horizon, composed of high-energy particles that would essentially incinerate any infalling matter instantly upon crossing.
Whoa, so instead of falling through smoothly, you hit a literal wall of fire.
That's the implication. While this would resolve the information problem, information never truly gets inside to be lost. It just gets burned up, and its remnants perhaps radiated back out. It directly violates a central tenet of general relativity, Einstein's equivalence principle.
The idea that falling should feel like floating in empty space locally.
Exactly. The equivalence principle holds that an observer crossing the event horizon of a large black hole should experience absolutely no unusual effects, no physical forces, just a smooth, unnoticed passage into the interior until they get near the singularity anyway. The firewall violently contradicts this smooth passage.
So instead of a smooth, unnoticed crossing, you'd hit a quantum mechanical wall of fire, a truly horrific fate that, however, saves the information. This raises a profoundly important question. Which fundamental principle are we willing to sacrifice? The preservation of information, unitarity, a cornerstone of quantum mechanics, or Einstein's equivalence principle, smooth horizon, a cornerstone of general relativity? It's a truly profound dilemma. What gives?
It is. And it underscores the immense depth of the problem. It really puts the conflict in stark terms. A third, perhaps more subtle path to a resolution was proposed in Stephen Hawking's final years, in collaboration with Malcolm Perry and Andrew Strominger. This work introduces the concept of soft hair, which subtly challenges the strict classical interpretation of the no-hair theorem that we discussed earlier.
Yeah.
Mass, spin, charge only.
Soft hair. Okay, less dramatic than firewalls or fuzzballs. What exactly does that entail? Is it a way to keep information without a firewall or a completely different structure?
The theory posits that black holes may possess additional, very subtle quantum properties, the soft hair, which are essentially low-energy quantum excitations, like very long wavelength photons or gravitons, living on or near the event horizon itself. These aren't like classical properties, temperature, composition, but are related to subtle symmetries of spacetime at infinity.
So extra quantum information stored near the horizon.
Kind of. This soft hair is associated with new, previously unaccounted-for conservation laws related to supertranslations and other asymptotic symmetries. The idea is that this soft hair could serve as a repository for information about the particles that have fallen into the black hole. According to this theory, as a black hole slowly evaporates via Hawking radiation, the information encoded in this soft hair would be gently imprinted onto the outgoing radiation, providing a mechanism for information to escape the black hole and resolve the paradox without resorting to a violent firewall that violates the equivalence principle. It attempts to find a subtle middle ground, modifying the no-hair idea just enough.
If we connect this to the bigger picture, these debates, fuzzballs, firewalls, soft hair, are clearly not just about black holes themselves. They're probing the very nature of reality, aren't they? Each solution requires us to rethink something incredibly fundamental about the universe.
Absolutely. Each proposed solution demands a radical reevaluation of our understanding of either general relativity or quantum mechanics, or perhaps even the nature of information and space-time itself. The various theories are not just different ideas about what happens inside or at the edge of a black hole, but fundamentally different statements about the underlying structure of reality, about how information behaves at its most fundamental level and about the ultimate microscopic structure of spacetime.
And we don't have the answer yet.
No. The fact that no single solution is yet widely accepted by the scientific community demonstrates that we are missing a crucial fundamental piece of the puzzle, a true unified theory of quantum gravity that can seamlessly reconcile these two titans of modern physics and tell us what really happens when gravity becomes incredibly strong on incredibly small scales. What's truly fascinating here is that these ongoing debates, the very existence of these unresolved conflicts, serve as a roadmap. They highlight the inconsistencies and tell us where the solution to this ultimate cosmic conundrum might lie, pointing us towards the next great revolution in physics. Black holes are the signposts.
So what does this all mean after our deep dive into these cosmic enigmas? It's been quite a journey. We've journeyed from the purely theoretical predictions of Einstein and Schwarzschild, through the core anatomy of singularities and event horizons, to the incredible direct observations from gravitational wave detectors like LIGO and the Event Horizon Telescope's amazing images.
A huge leap in just a century.
We've seen how black holes classify into a whole cosmic menagerie, stellar, intermediate, supermassive, maybe even primordial, and how they influence everything from the dramatic death of stars to the grand architecture of entire galaxies through these dynamic AGN feedback mechanisms.
They're not just sinks, they shape things.
We've had some truly profound aha moments along the way, right? From Schwarzschild's tragic brilliance and the no-hair theorem's elegant but paradoxical simplicity, to the forbidden mass gap being powerfully challenged by LIGO's groundbreaking discoveries,
That really shook things up.
and the EHT's iconic images that confirmed Einstein's predictions about warped spacetime in such a visceral, visual way. Black holes truly are the cosmic crucible for testing the very limits of our physical laws, driving us to confront the deepest questions about the universe.
And that profound tension, the fundamental clash between general relativity and quantum mechanics, particularly at the event horizon and the singularity, remains the ultimate frontier. It's where our current physics breaks. It's important to remember that the most fundamental questions, what truly happens at the singularity itself? Is it really infinite density, or does quantum gravity smooth it out? And how is the black hole information paradox ultimately resolved? These remain tantalizingly open.
So much still to figure out.
Definitely. This raises an important question for you, the listener, to ponder. What are the profound implications of these debates for our understanding of reality itself? Are black holes truly quantum fuzzballs, as string theory suggests, where information is never lost because there's no horizon in the classical sense? Or is there a high-energy firewall waiting at the event horizon, forcing us to rethink the very nature of space-time and gravity? Or will soft hair provide a more subtle escape route for information?
Which picture of reality is correct?
Whatever the answer turns out to be, black holes will undoubtedly continue to drive scientific inquiry for generations. They are the ultimate theoretical laboratories, pushing our theories to their breaking points and propelling humanity's search for a unified theory, a theory of quantum gravity that can finally reconcile all the fundamental forces and principles of the universe, revealing a deeper reality than we currently comprehend. They hold the keys, we just need to figure out how to turn them.